Okay, guys, today we're going to be talking about physical properties of matter and then a little bit about physical change, obvious, kind of in its entitlement. Okay, so before we can really start talking about the properties, we first must discuss or review really what is matter. So, matter is anything that has mass and takes up space. We've been discussing this since we started talking about atoms. So, something as small and microscopic as an atom to something as large as a whale, you're dealing with matter. Okay, but we can describe the matter in certain ways. So, a physical property is anything that we can observe or measure without changing the matter's identity. So if you talk about a piece of paper, you can talk about its color, you can talk about its shape, you can talk about how smooth or rough it feels, you can talk about how light it is. All of those things are physical properties. Okay, and you can change them and it's still a piece of paper. Okay, if I somehow uh, add ink to the paper, it's still paper. Nothing has fundamentally changed about it. Okay. So when we were to describe this cookie, okay, we might talk about its color. We would talk about its texture, whether it was hard or soft. What kind of smells did you get? What did it taste like? These can be all physical properties that we would use to describe a cookie. So our first one is color. Color refers to how light reflects off a substance. This again is a review because we discussed this when we talked about light and the electromagnetic spectrum. So color is what we perceive after it's been reflected off of an object. So the color of your hair, physical property. You tie-dye something, physical property. Luster. Luster is how shiny an object is. So you might describe this biscuit as maybe having kind of a dull appearance. If we were to add maybe butter over it, it might be a little more shiny. And then gold, if it was tarnished, you would say it's dull looking, but in this case, it's bright and shiny. So luster is how shiny an object is. Texture is how smooth or rough something is. So this basketball court has to be smooth, pudding generally smooth. Then you have things like rocks or a lizard. Those are rough textures. What's really interesting is a nail file is itself rough. But if you run that file over your nail, it makes your nail smooth. So it takes something rough to make something smooth. I find that paradoxical and interesting. Okay, odor. This is an easy one. Odor is just the smell of something. So if it's a skunk, it's not such a great smell. Coffee, my favorite, a very nice smell. So if you have me, you smell it quite often in the morning. Or it can be something like cologne. Some people put on too much. I know sometimes in the halls we get a lovely fragrance from girls when they're spraying their little body sprays to make them smell better. There are some days I wish boys would do that so they aren't so stinky after PE. Hardness. Now, this one's a little bit interesting. So you've probably heard that the hardest substance on Earth is a diamond. Okay, diamonds are very hard to shape. That is what we are describing hardness as. Okay, so it's its ability to resist change. So you may have a piece of wire that is extremely strong but easily bent. Okay, so strength and hardness are not the same thing. They can coincide. So things that are hard can be strong, but they are not directly related to each other. It's a correlation, but not a direct relationship. So conductivity. This one's an interesting one because you have the good and the bad. So there are times we want things to conduct. Okay, so a cast iron pan we choose because we know it will conduct heat well and cook our food. Okay, semiconductors, great at conducting electricity. Sometimes they generate a little too much heat, which is why computers and video game systems, things like that, have fans because heat is bad. And sometimes we don't want it to necessarily be such a good conductor. So water, great conductor of electricity, which can be bad, which is why if it's lightning, they never want you in the water because should lightning happen to strike the water, it's going to find you if you're in the pool. Then we have things that are not good at conducting electricity, which in itself can be a good thing. We use these properties to help us stop things from conducting electricity or heat. So if we look at that middle picture, the wire, copper, great conductor of electricity. Okay, but with electricity comes heat. So if you can imagine, if you have exposed copper all through your house and it's generating a lot of heat, that could be bad. Okay, so what they do is they add sheathing around the wire so that that heat and the electricity don't just freely escape. So rubber is a bad conductor of electricity. We use that to our advantage. Those oven mitts are made out of a material that doesn't conduct heat well, which is why you can hold something hot and it not burn your hand. And then a cooler or your Stanley Cups, ladies, are designed that whatever is in that object or whatever in the cooler or the Stanley Cup stays the same temperature. Okay. If we don't add anything to it, it will remain that temperature. If you put something hot in a cooler, it will stay hot, believe it or not. It seems ironic. Okay. But if we put something that we want to stay cold, if it's already cold, it'll stay for a while, especially if we don't open it. But if we want it to really stay cold for a really long time, then you add ice. And that cooler is an insulator and it keeps it cold and stops the ice from melting as quickly, depending on the quality of your cooler. We will talk about that soon enough when you design one. So, conductivity, again, is how well a substance allows heat or electricity to flow through it. You, as a person, are a good conductor of electricity, which is why people can easily be electrocuted. Malleability describes how easily a substance can be rolled or pounded into thin sheets. Okay, so think of aluminum foil. It's very thin material, it's rolled into it. Play-Doh can be rolled into a thin sheet. And then you can work iron into thin sheets or steel into thin sheets, so they are considered malleable. Now, some are more malleable than others and more easily done. So gold is interesting. It is extremely malleable, which is why when you buy gold jewelry, it's never pure gold because it would dent and scratch quite easily because it's easily worked. Um, so that's why it's often mixed with other metals to give it some of that strength that you would want. But gold can actually be pounded into really thin sheets. If you've ever heard of gold leafing, that's a really, really, really thin layer of gold that's been just pounded super thin that you can apply to things. Ductility, somewhat similar to malleability. This is probably one of those ones where you're going to want to focus on the difference, especially in the definition, because some things can be considered both malleable and ductile. Okay, metal is one of those. It can be pulled into wire really well, but it can also be pounded really thin depending on the metal. If you look at silly putty, that would be something that would both be ductile and then also malleable. Bubblegum, malleable because you can chew it, you can spread it thin. Okay, that's also ductile. If you were to keep it and then pull it out, you're going to get string. So when we say a wire, we mean like stringy. Would be something to keep in mind for that. Okay, magnetism. Again, something we've studied before. If you notice, we're now seeing a lot of overlap in some of the things that we've previously studied. Okay, so magnetism is simply the ability to be attracted or repelled by magnets. So if something's magnetic and it has a similar pole, it's going to be repelled. And if it has an opposite pole, it's going to be attracted. So that's kind of a simple concept we've already talked about. Solubility, this is a fun one. Okay, so when you dissolve salt, sugar, or Kool-Aid and stir it into water, it looks different. I will give you that. But it is actually still water and Kool-Aid mix. It's just now done really well. So, can Kool-Aid and water be separated? Yes. Is it practical? No. And here's a funny story. So last year, my students were convinced that that could not happen. So I put some Kool-Aid in water, and then I put it on a burner, and I let it boil and boil and boil. And pretty much the exact moment that all the water was gone, and we were left with just the Kool-Aid, I forgot what happens, and that's sugar burns quite easily. So once all the water was gone, all you're left with is food coloring and sugar. And that sugar burned pretty badly. And we ended up losing a beaker. So, can be done. Practical too? No. If you had the world's best microscope, you would be able to actually see the separate particles. It'd have to be really, really good microscope. But it's definitely not something that we can see with our naked eye. But an easier example would be something like salt in water. You can dissolve salt into water quite easily, and then you can easily boil the water away and be left with those salt crystals. So solubility is how much as an object's or a substance's ability to dissolve into another one. Okay, sugar and milk was something that I had a lot of when I was little. You would see like the little sugar flakes, or if you've ever had cinnamon toast crunch, you see all that cinnamon just mixed in with the milk at the end. So it's not a new substance; they're just dissolved inside of it. Okay, melting point. So that is the temperature at which a substance begins to, not completely, but begins to change from a solid to a liquid. Now, if we only stay at the boiling point, it will actually never fully, a melting point, it will never be fully melted. Okay, you actually have to go a little bit past the melting point to get it to fully melt eventually. And the further you move away from the melting point, the faster it will melt. Okay. So here you have probably iron that's in its starts out solid. Then they superheat it till it becomes a liquid, and then they pour that into a mold and then allow it to cool, so to go beneath the melting point, and it becomes solid again. The boiling point of an object is the temperature at which the substance will change from a liquid to a gas. You've seen water boil, I'm sure. It doesn't all boil at once. It takes time, and depending on how much water you have, it can take a long time before it boils away completely. Okay, and that's the beauty of it, though, is you can get boiling water, say for tea, and still manage to get it hot enough to where that's what you want, but you still have water left. Because if it was instantaneous, that would be a bad thing and not productive for what we have. Okay, so boiling water for tea, it's turning into a gas, but not everything is becoming a gas all at once. Okay, density. You have a golf ball, and it has a certain amount of mass and a set volume. Okay, that's its density. Here you have a marshmallow. It too has a certain amount of mass in a given size, in a given volume. Okay, I would argue pretty confidently that a golf ball is more dense than a marshmallow. Okay, it's why a 10-pound bowling ball versus 10 pounds of feathers would be considered more dense because that 10 pounds in that bowling ball is going to be in a much smaller volume than 10 pounds of feathers, which would take up a lot more space. Okay, and that's where density comes into play. Hey, also interesting. If you are less dense than water, you will sink. No, sorry. If you are less dense than water, you will float. If you are more dense than water, you will sink. So less dense, you float. More dense, you sink. And that's actually true for most liquids. We'll do something later on to demonstrate that as things are added, especially if they're liquids or even solids within liquids, they will arrange themselves automatically by density. And so we will demonstrate that. It's a pretty cool experiment. So a physical change is a change that affects one or more physical properties. What it does not do is create a new substance. Okay, so what we saw in the conservation of mass lab were not physical changes because we ended up with completely new substances. Okay, it is just that a property has changed within that object. Okay, so if I chop a piece of wood or I sand a piece of wood, I'm changing a physical property. So that's a physical change. If I light that wood on fire and burn it until it is nothing but ash, carbon dioxide, and smoke, or that is a chemical change. We've actually changed the substance. Okay, if you take a red shirt and you bleach it, well, that's a bad example. We're gonna do the opposite. We're gonna take a white shirt and we're gonna dye it red. It is still a shirt, and all you've done is change the color. If you polish shoes, you've changed its luster. That's a physical change. You've changed a property. Okay, it's not a completely new substance, and that is something that is important. Okay, so if you have wind and water erosion, okay, this is a physical change. The Grand Canyon is an example of a physical change. The Colorado River has run through the Grand Canyon for I have no idea how long, and it has slowly moved rock out of its path and worn itself down until it's in this large canyon. Okay, the rock still exists. The rock is still the same. It's just been worn away. Okay, same idea with, say, piece of wood and sawdust. That species of wood from that sawdust is still the same species it came from. It's just a smaller part of it. Okay, you've changed maybe the smoothness or the texture of it, but in itself, it's still wood. So that is something to keep in mind. So chemical changes are what we're going to talk about next, but not in this video. That will be another set of notes. But something I want you to think about. I want you to think about 10 different physical changes that you can find pictures of, and you need to explain what the physical change is and what property was changed. Okay, so you'll see that as an assignment, as a slide show in Google Classroom, and do your best to complete. Thank you.